So today's lecture is about how to interact with the outside world. How does a Haskell program talk to the rest of the world? I want you to think about something for a minute, and that is whether A plus B is equal to B plus A. Let's suppose we're talking about numbers here, some reasonable kind of numbers. It's a property, a mathematical property that we expect to be true. Now, programs that you write also contain plus operations, and admittedly in many languages these are overloaded, but ignore the overloading issue for the moment. Just think about adding various kinds of numbers together, and ask yourself the question whether A plus B is equal to B plus A in your favourite programming language. Well, what does that mean exactly? Well, can you take a program that you've written, which contains A plus B, and replace it with B plus A, where A and B are some arbitrary bits of program? And the answer is almost certainly no. For example, if I wanted to add f of a function called f and a function called g in your favourite language, then we may know that f and g return, let's say, integer values, and we can add those integers together. But what we don't know, on the face of it, is whether those functions return those values by interacting with the outside world, for example, getting a value from the user, or randomly generating a value. And so what that means is we can't be sure that the behavior of f plus g will be the same as g plus f. Maybe that's not so surprising. Is that a bad thing? Well, it could be a bad thing if, for example, we would like, when we see this, to think, we can maybe evaluate this on one core and evaluate this on another in parallel and add the results together. We can't necessarily do that just by looking at the functions, or at least looking at their types. We'd have to know about what side effects they might or might not have. Haskell expressions, Haskell programs, are in a certain sense free of side effects. There are no side effects. Now that may seem strange, but in Haskell, functions, when we say we're defining a function or a value, you can think of a value as a function with no arguments, these are real functions in the sense that whenever you apply the same argument to a given function, it will always give you the same result. That's the definition of a function. It has a single valued result. Okay? So they're functions in the mathematical sense. That's not true of functions which are defined in most other programming languages, because there is a hidden state, the state of the world, which affects the result that a function call might give you. A simple example might be, you could type something like this in Python. This is not equivalent to 2 times input, right? And why is that? Well, because each call of input produces a different value, potentially. And why is that? Well, because it obtains a value by interacting with the outside world. So then the question is, if I've told you now that Haskell functions are pure, they're real functions, then how can Haskell programs interact with the outside world? That's what we're going to learn about in today's lecture. How do we keep pure and still have the opportunity to interact? Okay. We can run a Haskell program and it can do all kinds of things. And the first question you might ask is, what's the type of the result? Well, let's start much simpler than that. Let's start with some small examples. For example, writing values to a file. There's a function called writeFile, which will write a given value. There's a value, a string, and put it in the file that we want. In this case, it's a text file that I'm going to create. And what does it do? Well, it doesn't appear to do anything. It doesn't return any value at all. Has it actually done anything? Well, if we list the files in this directory, let's have a look. There we have hello world. Oh, it looks like I've got the arguments the wrong way around. Let's do that the other way around. I should have asked about the type, but I don't want to ask about the type just yet. Let's do it that way around. That was probably a bit more sensible. And let's have a look what we've got there. As well as my strange file, I have got this file here. If I have a look at it using it does indeed contain hello and then world, and it doesn't actually end on a new line either, which is why the command prompt starts immediately after the file. Okay, well I might have not made that mistake if I'd asked what the type of that thing was. So I can ask what the type of the write file function is. And here you might see a type with some stuff that you don't recognize. The first thing is a file path, and the second thing is a string. How did I manage to get them in the wrong order? What is a file path? Actually, a file path is just a type synonym. It's another name for a type we already have, namely a string. So wherever you see string, you can, if you like, use file path and vice versa. So all it does is give you a little bit of documentation about what this function does. It doesn't actually constrain the way you use it. It doesn't stop me from writing the string where I had the file path and the file path where I had the string. That's all very well, but it's a function with two arguments, as you saw, and this is the type of the result. This is the result where you saw nothing on the screen. So what does this mean? Well, I/O is the type of computations. It's the type of instructions which, if you run the instructions, will interact with the operating system, with the runtime system of GHC in this case, and potentially produce a result. In this case, the result that I'm potentially producing is the void result, the null, the unit type. And so that's not printed on the screen. So that's a non-interesting result produced by a computation that interacts with the outside world. Okay? So there's a special type for things which interact with the outside world. So why is that? Well, here's a rather silly analogy. If I have a list of instructions, in this case a list of instructions for taking a bankomat card, cash card, and getting some money out from a cash point machine, obviously the instructions and the effect of running the instructions, the effect of following the instructions, aren't the same thing. Instructions and the result of doing the instructions are not the same. Okay? Now, it sounds facetious, but the point in Haskell is that there is a distinction made between the type of instructions for interacting with the operating system and the result of running the instructions. So you should think of I/O as being a special type, an abstract type, representing instructions. So functions that would produce something of type I/O are pure functions. Whatever arguments they give them, they will always give you the same instructions. But of course, running the instructions may give you different values depending on what day of the week it is. If you run the instruction on the day before payday, you might not get any values out. You might not get any dollars out. But if you run it after payday, you may well get something. But the instructions remain the same. Okay? So the idea then is that I/O represents the type of instructions. Let's take another example, and that's the read file example. It's also a function with an argument, which is a file path, as we know, just a string. And it results in instructions for producing a string. Okay? And every time you apply it to the same file path, you will get back the same set of instructions. But of course, if you run the instructions, you get different things depending on when you run them and on what machine you run them. So the distinction between building the instructions and running the instructions is what allows us to think of Haskell as being a pure language. Now, the crucial point here is that who gets to run instructions? Is there a function called run instructions? The answer is no. There is no way of running the instructions from an arbitrary expression. The only way that instructions get run is if they are the top level value that is returned by a Haskell computation. So if the result of a Haskell computation is something of I/O type, then the runtime system will actually run the instructions. That's the only place where instructions get run, is when the I/O type reaches the top level. A value of top level of I/O type gets run by the system. Any question?
Yeah.
Yeah.
Did they have some kind of file path for standard error, standard input?
Yeah, there's. So I'm going to talk about, in this lecture today, I'm going to talk about I/O, but only in a very superficial way, in the sense that if you were a systems programmer, you'd be very unhappy about what I'm going to say, because I'm not going to get into details. There are pretty big libraries about various kinds of I/O where you can do all kinds of the things you might expect to be able to do with I/O. I'm really only going to barely touch on those. I need to just get across the basic concepts of I/O. So there are indeed various ways of getting a fine-grained control, having definitions for standard input, standard output, and so on. I'm going to use very high-level primitives which hide all the lower-level details away, but they are accessible in the libraries. Okay, so if, as in this case, we have some instructions which can produce a string, the question is, how do we get the string out of the result of this I/O? And the answer is you can't. There's no function in Haskell, in pure Haskell, which will take something of type I/O string and give you back the string that was in the I/O. And why is that? Well, if you could do that, you would break this purity that we have. You could have functions which run some commands and return a string, but if you run it on Monday when there's something in the file, one thing in the file, you'll get one answer. You run it on Tuesday, there'll be something else in the file, you'll get a different answer. And that'll be something which is hiding the fact that it's interacting with the outside world. So there's no way of hiding the fact that you've interacted with the outside world. So the only way to use the string that's inside the result of an I/O is by using it in the context of some other I/O. So we will see today building blocks for building things of type I/O, which would allow you to use the strings returned by, for example, read file. Okay, it's all a bit abstract, so let's actually do a little bit of coding, because I think it'll get a bit more concrete. Please ask questions as we go along. Okay, so we just looked at write file, and we just looked at read file. So if I, for example, read file, what was the file we had earlier? It was ex something or other, ex1.txt, and it contains the string that we expected. Now, what if I wanted to read the contents of one file and write it to another? You might think, well, we need to write file. Let's write to the file ex2 the contents of ex1. And what was that? Well, that was read file of ex1.txt. Okay? It doesn't work. Why doesn't it work? Well, the result of a read file is not a string. The result of a read file is an I/O string. Okay? In other words, it's a string which is obtained by interacting with the operating system. It's an instruction for producing a string. And as I said before, we can't just simply pretend that this thing is an ordinary string. It's not an ordinary string. So that means we can't apply this function, which is expecting a string as its argument. So we have to see how we can get around this. So this is the basis of what we're trying to do is copy one file into another. Now let's define that as an operation, a function called copy file. What does copy file do? It takes a file path for the first file, a file path for the second file and produces instructions for copying the one file to the other. So that's the expected type of copy file. So what does copy file do? Well, we have to introduce our first non-primitive building block for building things of type I/O. We've seen a building block, namely read file and write file, which would result in things of type I/O of something. Now we need to see how we can put these together. And the simplest way we can put them together is by a bit of syntactic sugar called a do. So do, I'll start on the next line. A do block is a block, that is to say an aligned sequence of expressions. Each of the expressions is of one of two types. They all involve something doing I/O in this case. So here we have read file. Copy file has two arguments, I forgot to name them. From file and to file. We read file from the from file. Now we need to do something with the result of this. So the result of this will be a string in the I/O type. So we need a way of naming that string. So the way we can do that is with the following syntax. The contents C, we get the contents C from the result of running this instruction. That's the first line. And then what we're going to do is to write file those contents into file 2. And I think I've got them the right way around. So now this is a program which consists of, it's a do. That means it's going to build something of type I/O. The first line does an I/O of string and gives the name to the string, calls the string C. The second line uses the string C to do some other I/O, namely something of this type. And the last line, the type of the last line is the type of the whole do block. Okay, so this is a sequence of lines resulting in something of, in this case, this type. And in order to get something of this type, the last line of our do block needs to have this type.
I have a question.
Yes?
Isn't C IO string here?
No, it's not an IO string because this is a special syntax that I'm introducing.
So that is converting from IO string to...
It is, yeah. And you say, well, I just told you, you couldn't get a string out of an IO string.
Yeah.
Well, the thing is that you are getting a string out of an IO string, but you're doing it inside a do. So whatever you do here with this string, the only thing you can ever return, because it's inside a do, will be an IO of something. So there's no way of getting this. I'm getting this string out locally, if you like, inside this do block. But I can only do it inside the do block. And that means the do block is saying, well, whatever you do with that string inside, the end result will still have IO on it. So the only place you can do this is inside the do block. And the do block then guarantees that there'll be an IO on the result.
And the write file can handle the C.
Write file, so C has type string. But the result, you can only use that string inside something of type IO of something. And that's because you can only use this operation inside a do block. And every do block in today's lecture will give you something of type IO.
But how Haskell know that C have to be a string?
Well, it does type inference. That is, it looks at the evidence available from the program I've written to work out that it needs to be, that it will be a string. For example, it knows the type of this is IO of string. That's one reason it knows that C should be a string. And what's more, it knows that the second argument to write file has to be a string. So everything matches and Haskell is happy. So the general syntax is that you have a variable and something, and so the type of the variable, let's suppose the type of the variable is A, then the expression here has to have type. So if the variable has type A, the expression has to have type IO of A. And the last line, the type of the last line will be the type of the whole result. In this case, it's an IO. Let's just try that out. Oops. If we reload that file, we can copy file, the contents of ex1. We better make that into a string. Into example 3. Nothing to see. Of course, when we read file, we can see what it produced. ex3. And it was indeed the original value that we had in file 1. Any questions about that?
What did write file return? An IO. If we only call the write file.
The type of write file takes a file path, a string, does some IO and returns nothing. So it's a, if we run it, it'll be silent. Yeah.
Could you return something like status integer or something?
Yeah, that's a good point. So in general, that's one of the things that the IO library will contain is operations that will tell you if you're doing some interaction what the status of the result is.
What I mean is the function copy file, can we have a return type of int somehow and have this IO stuff hidden in there?
Yes, we can, but we would have to use, we're using very basic, simple IO primitives in today's lecture. You'd have to dig into the IO libraries to find the ones which are underlying these, and they're the ones that will return exit status for non-existent files and this kind of thing. Okay. So as I said earlier, in response to the earlier question about the details, we're not really going to dig into low-level IO stuff. It kind of does the things you would expect. We're just going to keep things very simple today. Yeah. Okay. Any questions? All right, let's take another example. Let's suppose I want to find the longest word in the dictionary file, which is on my machine here, standard Mac location for the dictionary file, Unix style, is in user share dict words. So our job is to find the longest word in this file. So what's the type of longest going to be? It's an IO string. It's something which is going to interact with the operating system in order to read this file and produce a string as a result. So the type of this thing will be IO string, and it's something which we could use in other programs of type IO. But we couldn't use it in a program which didn't have an IO anywhere. We couldn't hide the fact that this function has interacted with the outside world. So what is the longest going to do? Well, you notice here I'm starting on the next line. It doesn't matter where I start. The main thing is that all the lines in a do expression have to be aligned in the same column. That's our brackets, right? Aligning in the same column. So that can be a source of tricky bugs. Another source of tricky bugs is if your editor, your text editor, uses tabs. Your text editor shouldn't use tabs. It should only use spaces. Because a tab may have a visible appearance of, say, 4 spaces, but actually only counts as 1 character. So when you think that something is lined up, it's actually not lined up. It's just that your editor is displaying a tab as a wide thing and not as a single character. Okay, so that's a little warning that some of you have probably already been bitten by. So I apologize if that warning is later than it should have been. Okay, back to the longest. Obviously we're going to read file and we're going to read this thing here. And if we're going to do anything interesting with it, we better give it a name. So that's the word list that we're going to get from performing that operation. What are we going to do with that word list? So word list now is a string, but of course it's inside a do, so we're never going to escape I/O. We need to find the longest word. So let's do that computation as a pure functional computation. Finding the longest word in a big string, we'll treat that as separate. So what we want to do now is give the result of computing the longest, let's call it long, and make a local definition. So long, we'll take a string and compute the string, the longest word in that as a substring of that string. Let's just make it undefined for the moment. Okay. So now my do block gets the contents of the word list and then is computing with some function we've not yet defined the longest word. So let's compile that, and we see we have a problem. We couldn't match the expected type of IO string with the actual type of string. What we have here, according to our declared type, is that this thing should be of type string, but what you expect, the last command of a do block should have the same type as the whole do block. So if we want the whole do block to have this type, the last command should also have this type. So we have something of type string, and what we need is something of type IO of string. So we need a way of taking a thing and turning it into an IO of thing. Okay? Now I said we couldn't go the other way round. Can we go this way round? Well, the answer is yes, we certainly can, and there's a very small function, but a very useful one, for doing that. It's called return. So return, in this context, will take a thing, in this case a string, and turn it into an IO of string. So this is a trivial, return is a trivial computation. It produces a value without doing any computation at all. Okay, so that's one of the most basic computations. So if I return 42, the type of that is IO of, let's say, int. And it produces, it's an instruction for producing a number without doing any work at all. But it's still an instruction. Question?
Can you show us the type of return?
I can show you the type of return, but it will be a little bit more general than you would expect. So I'd like you to think of return as having the type A to IO of A. In fact, it's more general than that. This M here, we're using it when M is IO. So we're doing something which has an A to an IO of A. Okay, so what this is actually revealing is that everything we're doing today with do and returns and do blocks and all this other stuff is actually much more general than IO. You can think of it as IO is not the only kind of instructions out there. You can build your own instructions of your own types. But today we're dealing only with instructions for interacting with the operating system. But in fact, these are things which have much more general types. There's a class called monad, and IO is one of the things in the class monad. Okay, that's how we would compute the longest. Of course, we actually need a function to define how to compute the longest word in a list. So we have our string, and we need to break it into words, and then we need to find the longest word. So you might think, well, maybe maximum would do that. So you remember words, I guess. It takes something like A, B, or it might be new line characters C, and splits it into its words. In other words, splits it at every space or new line or tab or whatever character. So words will give us our list of words, and then we want to take the maximum. Now, is maximum the function that we want? What is the maximum of oh, what am I doing here? What is the maximum of well, let me say A, BB. If we take the maximum of that, that looked all right, didn't it? What if we did AAA? So clearly maximum is not doing the right thing here. What is maximum actually computing here for strings?
Lexicographically.
Yeah, it's producing the last string in the lexicographic order. It's the last string in the dictionary order. That's what you would expect max to do. So that's not what we want. What we want is to compute one of the longest strings. Okay, so what's a good strategy for computing that?
Map with length.
That's an interesting strategy. So you map, the suggestion was we do something like map length on to, well, let's take what we had before, which was words of that. We map length, we get a list of the lengths, and we can take the maximum of that. We could take the maximum of that. Would that give us the answer we want? Well, no, we actually want the word that has length 4, not the length of the longest word. So that will give us the length of the longest word. Here's an idea that works using the fact that this maximum function is polymorphic. It takes anything which is ordered, a list of anything which is ordered, and gives you the biggest. So what things are ordered? Well, loads of things are ordered. If you build a list of ordered things, they become ordered. Char is ordered, that's why string is ordered. Another example is if we take a pair of things which are ordered, the result will also be ordered. So what we could do is, instead of mapping length, we actually can build pairs of things. If we actually pair length together with the word itself, so we actually make a function out of this, it takes a word and gives you the length of the word and the word itself. Okay? And we see that what that's going to do. It's going to produce, this is going to produce a list of pairs with the length followed by the word itself. Then when we look for the maximum, the length will be like the first letter of the word, as it were. The length will be the main thing we will sort on. And so then you see that we have a length 4 word with 4 A's. So how do we get the result we want from that? We just need to take the second element of the function second, which takes the second element of a pair. So I'm doing this sequence of computations, and we get the maximum. So what is that sequence of things? Well, that sequence is just a composition of a bunch of functions. We paste that up there. We don't need the S here. We can just do it by composing this as a sequence of functions. We compute the words of the string, turn them into a list of pairs with length followed by the string, find the maximum of those, which will give the alphabetically first longest word in the sequence, and we extract that from the pair by doing second. Does that compile? It compiles. Are you excited to find out what the longest word is? The longest word is, it's pretty big. Thyroparathyroidectomize. I hope you don't have to have one of those. Sounds like some nasty operation involving your throat. Interesting. All right. Any questions?
So the do block kind of separates the pure world from the impure.
That's a good question. So the question was, the statement was that the do block separates the pure from the impure world. And the answer to that is actually no. It requires good programming to separate the pure from the impure world. So there's nothing to stop us from piling all this pure computation inside the do block. But it's good programming style to keep them as separate as possible. Why might that be? Well, one reason is that it's much, much easier to do testing in a pure world. We can use our nice tools like Quick Check, for example, to do automatic testing. It's much harder to test when we have interactive programs. So if you can separate your code into pure functional code which doesn't deal with any I/O, and a small part of I/O, which kind of is the shell which just interacts, that interfaces to the outside world, then your code becomes much easier to test. But that doesn't happen automatically. That requires programming discipline and good programming style. Okay, now it turns out that things of type I/O of whatever are first-class citizens. They are not special in the sense that we don't have to treat them in a special way. What that means is things of type I/O can be part of arguments or parts of results. Just like functions are first-class citizens, things of type I/O, in other words, instructions, are also first-class citizens. Here's an example. The function do twice will take as its argument an I/O thing and compute it twice. First time it will return an A, the second time will return another A, so the result will return us a pair of A's. So a function do twice of that signature, you give it some instruction as an argument, and what does it do? It runs the instruction once to get the first answer. It runs the instruction a second time to get the second answer, and then returns the result, which will be the first answer and the second answer as a pair. Okay, so here we're using this thing as type I/O, and remember what I said about the do block. The thing on the right-hand side of one of these has to be an I/O of something, and that means the type of this will be a something. So this is an I/O of A, this will be of type A. This is also an I/O of A, and this is a type A. And this thing here is of type I/O of the type of this thing. Let's run that on something. Let's read file from our example. So what do you expect to see? Well, you get the result of reading the file and the result of reading the file again. And of course, the file has not changed in between the two readings, so we get the same result twice. But of course it might, if somebody else had written in between, it might have actually got different results on each time it ran it. Okay, let me look at one more example then before we take a break. And that's the function don't. We've seen do twice. Let's see a function that doesn't do anything. It takes a computation of type A and doesn't run it. What's a good type for don't? I'm just going to have a look at the lectures. What is it going to do? Well, let's say it returns an I/O of nothing at all. So if I give it an instruction I, what should it do? Well, it shouldn't run the instruction. Sounds pretty stupid, doesn't it? The only thing we can really do is just return this to get our I/O of A. What's the point of the example? The point of the example is to emphasize that there is a difference between having an instruction and running an instruction. So if we don't, and then that thing, if we don't read file, then we're not going to read the file. So the point is that it won't actually run the instruction. Just because it is that the instruction is there doesn't mean we'll run it. Instructions only get run when they meet the operating system. That is to say, when they meet the runtime system of GHC. This I here never gets to meet it. It's an argument to this thing here. So for the moment, it's just an abstract data type, which is never used in the result. Question?
So the read file function is never called here.
It's never called.
Shouldn't the read file be called before the don't function is called? Should you read the file? Example?
No. The type of this thing is an IO of string. That's the type of an instruction. So what you can think of is what we're doing is building the instruction for reading a file. And we're passing that instruction as an argument to the function don't. And what does don't do? Well, it doesn't do anything with it at all. It builds this instruction, which will be then run by the runtime system. And of course, running the return instruction doesn't give you anything interesting. Now, in the last 30 seconds, let me just give you one example just to show that return is not like the return that you're used to, a control flow structure. Return has nothing to do with control flow. If I have a test example, just an example, which does the following things. So that's a perfectly good program. It has type IO of, let's say, int. Let's call those ints. The first line has an IO type, which it has to have. It has type IO int. The second line also has type IO int, and that's the type of the return for the whole thing. So what happens here when I run it? What value do I get? Do I get 42 or do I get 0? We get 0. Why is that? Well, this is just a trivial computation that returns a value 42. It's nothing to do with control flow. It doesn't say, oh, and stop this function call. All it does is deliver the value 42. We could give that value a name. The answer is 42 and not use it. So now we've got we've returned the value 42 and we've given it a name, but we've not used it. Doesn't make any difference. Doesn't change what the program does. Namely, it does a trivial interaction with the outside world. Well, no interaction at all. And then it does another trivial interaction and returns the value 0. So return is not a control flow construct. Okay. All right, so we have an opportunity for a break now. And during the break, I'd like to think about the following functions. I haven't given you the example of the function sequence yet, so I'll do that shortly. But you'll probably work out what it does from its type. So if you want a little exercise during the break, be my guest. And we'll be back at 1:15.